Hello all, welcome to this tutorials in which we'll be looking at implementing DDIMs. Now, whenever I mean implementing DDIMs, what do I mean by that is just inferencing using the DDIM method. Now, why are we not training anything? Because it is evident from our theory sessions that now if you are training a regression network in DDPM, now, it is implicitly training an infinite family of non-Markovian models which are needed for our DDIMs. Now, in the current case, I'll be going ahead with the noise estimation model, which we have seen in an earlier tutorial as the base model, and then we'll be going ahead of it and then obtaining the samples in a DDIM process. Okay. The only thing that we shall be doing now is inferencing using the DDIM idea. Now, please recall from the DDIM discussion that so whenever you are performing a sampling, now it is having three parts. Now, one is this is one part, now this is another part, this is another part. Now you need to add these three parts. Okay, now we will be getting each one of them separately and then finally we will be adding them. Let's look at the code now. Okay, now these are the generated images for DDIMs. They're good. I don't say they are the best, they're good. Okay, so now let's go ahead with the DDIM implementation. Now I'm calling the DDIM sampling. So I'll be giving the number of samples as 16. I need 16 samples. So I'll be sampling for 30 time steps. So now if you're doing ahead with DDPMs, now if the model has been trained using 600 time steps, you need to go in a reverse order for all the 600 of them. Now in DDIM, that is not required. Now you can say that, okay, now I'll be only going ahead with certain amount of time steps here for 30. Now eta should be 0. Now please go ahead and try for the full time steps and eta equals to 1 and compare the results. So now coming back to DDIMs, now this is what you want. Okay, now you have put in the evaluation mode. Good, you are taking all the timestamps. Fine, that is what the first thing that we wanted. Okay, and then you are putting in a reverse order and converting it into a list, and then finally you are taking the adjacent timestamps like T0, T1, T1, T2 like this, which represents current and the next. Now because at any given point of time, now we will be needing the next time test step as well as the current time step. So we will be needing them in pairs, okay, as per the need of the equation. Okay, so now first you sample a standard Gaussian noise. Okay, now then we need to go ahead with the DDIM sampling. Okay, now first you obtain the time, fine, and then you pass the image and then the time to obtain the predicted noise. Okay, this is a noise prediction method that I shall be using. So you have got the noise needed. Now then you have got all the alpha bar t next and all those things. Now you are actually obtaining this mu theta star. Okay, now please look at the mu theta star equation. Now in this I have given it as predicted x0. Yes, even that can be the case. Now if you are predicting the noise, now this can be the predicted x0. Now you can look at the similarity now between these equations. Now xt, which is the image that you have, minus now 1 minus alpha t, okay, into the predicted noise, now divided by the square root of it. As you can see, now that is being done, image minus a square root of 1 minus alpha t. Yeah, now here alpha t always means a bar. Okay, that has been discussed in the theory as well. Now, whenever I mean alpha t, I always means alpha t bar. Now this is as per the the theory, it is as per the literature. But here I have preferred to go ahead with the existing terminologies which we have used earlier, so that it will not be having issues with the training procedure and then the inference procedure using DDIM. I have left it as it is. Okay, so you have obtained this, which is nothing but the predicted mean. That means that you have got this. Okay, and then you can get this also. Now this is very easy to get. This is a cumulative product. Now and then this is the predicted noise. Okay, you have got x0 and then you clamp it. Now all those things are the standard procedure. You get the predicted noise into this term, square root of 1 minus, so alpha bar t. Okay, as you can see, this is mu theta star that you have got. Now this is the thing, this is the predicted noise. Okay, and then this is that multiplication that you are supposed to do. And please remember that the equations this and this are very similar. Okay, now obtaining one is same as obtaining another, and as I have told you, now here alpha t always means alpha t bar. Okay, so now you have got this, and then you get this term sigma. Okay, now what is this sigma? This term. Okay, 1 minus alpha t minus 1. So there is a square root, so you can take the square root common altogether, and then you can have this. That is what is being done here. The whole product has been calculated. Okay, and then you multiply it by eta. Okay, now why do you multiply it by eta? Now the reason is, if eta is 0, now which is an indication of DDIM, so we just want to take it into consideration and have this. Okay, now since we have 0, now this will become 0. Okay, now, but whenever we have et equals to 1, I want you to look at the outcomes and see. Okay, so now you have this part. Okay, now which is sigma into noise has been become 0 now because of my eta as 0. So now, and then you have obtained the direction. This is the direction that you have obtained. Now, how did you get it? You can see that this is square root of 1 minus alpha bar t next, which is this. This will have eta, now because of which it will become 0. This into the predicted noise. That is what you're getting here. This is called as direction of xt. You're adding all of them. Now this is the image. Now this you're repeating now for the time pairs that you have got. And finally, you clamp the image to get it in the presentable format. Okay, now please remember that. Now this is the equation. When eta is 0, this term and this terms are gone off. Now because of which this is the predicted mean. This is the predicted noise. Now from the predicted noise, you can get the predicted mean and then perform this operation. That is what you have done here. Now using which you have obtained the images with almost 10 times of the sampling process. Okay. Now normally, even if 20 times reduction, even if you have taken the time steps as 600, now you are only sampling it for 30 time steps. So there is a reduction of 20 times. Now this is a very nice operation. Okay, so I urge you to rerun this with modified parameters and get a crisper and sharper images. Now with this, now we will conclude our tutorials on DDPMs. In the next tutorials, we will be looking at weak tense contents, which is autoaggressive models. Thank you.